In this lecture, I am going to review the derivative function. Start with the definition. The derivative of function f is a limit. Okay, we denote it as f prime of x. F prime of x. And this is a limit. So to talk about function, first we need to know where it's defined. The domain of f prime, the derivative function, is where pretty much this limit exists. So the domain of the derivative function, you pretty much start with the domain of f. But on the domain of f, there are certain points, there are certain x values that this limit does not exist. In that case, you lose those points from the domain of f prime. So the domain of f prime it could be smaller than the domain of f, but it cannot be bigger. Now, what is the derivative? Here I'm showing you several ways of, pretty much why we do all this to get a new function from function f to f prime. F prime, by the way, is another function, okay? You start with f. Normally, most of the cases, you get a different function. And here I'm showing you several ways of understanding it. The first is geometrically, and that's the picture I'm showing you. The value of f prime of x can be interpreted geometrically as the slope of the tangent line to the graph of f at the point x f of x. So in the picture here, the black curve is the graph of f. And when you pick a value, say a, you get this point on the graph, right? A f of a. You choose x to be a, or x coordinate to be a. Since you have a curve, you can draw this tangent line, which is the red line that I'm tracing. The tangent line is the line that only touches the graph once. So for example, if you have a parabola, then pretty much this is the tangent line, and another tangent line, another tangent line, and another tangent line. So the line only touches the graph once. This is not a tangent line because it touches the graph twice, okay? So all those purple are tangent lines. Okay, and when you have a line, the tangent line is a line. A line has a slope. So the derivative actually is the slope of the tangent line at this particular x coordinate in here, a. Okay, so if I pick another point on the graph, say here, I draw another tangent line. Well, I don't think that's a very good drawing. I think that's better. Then the slope of this line will be, let's call this point B. So the slope of this line will be f prime of B. This will be a negative number because this line that I just drew is falling. But anyway, the point is the derivative function represents the slope of the tangent line to the original graph of f at particular x coordinates. And then, of course, if it doesn't exist, it doesn't exist, which means the derivative at that point is not defined. Another way of understanding derivative is it is the instantaneous rate of change of y equals f of x with respect to x, with any pretty much x value. So at this particular x value, how fast y equals f of x is changing. Okay, in particular, if you view it in physics, then it will really be like x coordinate will be time. So instead of x, we call it t. And then the y coordinate, here it will be s, will be the displacement. So it's like a particle moving along a straight line, and here's your particle. It goes here, 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 like back and forth. Or maybe just one way, doesn't matter. The velocity, meaning speed, but with direction, positive or negative. The velocity of the particle at any time, how fast this particle moves, okay, is the derivative. So these are the interpretations or understandings of the derivative. In particular, I would say the geometric way is very important. Okay, you really need to understand. That's why I'm having this picture here. The slope is, the derivative is the slope of the tangent line. The slope of tangent line. Here are pretty much all the formulas that we have learned in Calculus 1. So let me go over them one by one. First of all, when c is a constant, the derivative is 0. So derivative of constants are 0. Constant means not changing, and derivatives is rate of change. When you have a rate of change of something does not change, you have no change, which means 0. Then this is a bunch of, the following are a bunch of derivative of operations. When you multiply a function by a coefficient or constant c, pretty much you can point it out. The derivative of a constant times a function will just be the constant times the derivative. Similarly, the derivative of sum or difference will be the sum or difference of the derivatives. Okay, so when you multiply by a number, or you add or subtract two functions, and if you want to get a derivative, you can pretty much, push the derivative inside into the core function, f of x or f of x and g of x. But it's not true for multiplication or division. When you are differentiating a product, f times g, what you do is first product times derivative of second product plus second factor times the derivative of first product. Okay, so first factor times derivative of second factor plus second factor times derivative of first factor. So each time you differentiate one thing. Actually, it doesn't really matter which way you go. You can differentiate it. You can take the derivative of the first factor first, right? Because addition, you can swap them. But you can't swap them for the quotient. In quotient, you need to make sure. Normally, I suggest my student do the quotient rule this way. You write down the denominator first, the square of the denominator, and then you do that denominator again. Okay, so start with the bottom. The bottom is the square of the original original denominator. Then you do denominator, numerator, taking derivative. Then you switch numerator times denominator, taking derivative. But the thing is, if you write the denominator squared first and then repeat, you copy that same denominator one more time, you won't mess up with the two products on the numerator, here on this numerator. In particular, when you take f as 1, you will get this reciprocal formula. So pretty much is the same formula with quotient, but the numerator f is 1, which is a constant function. So when you have constant function, what happens? F prime equals 0. So this whole thing is gone. And f is 1, right? So you get sorry, I missed G prime. Somewhere you have to have the G prime. Okay, so that's the formulas. In other than all these like basic rules, we have one more formula, which is the power rule. Power pretty much is like the foundation of polynomials. So the power rule says when you are differentiating a power of x, the independent variable is on the bottom, okay, on the base. Then what you do is you copy, well, you will see me switching the prime notation and the ddx notation a lot. So when you are using the ddx notation, you're emphasizing what you are what is the independent variable, what you are differentiating with respect to. But when you use prime, it's much shorter, right? So when you take derivative of x to the n, this is what you do. You pull the exponent to the front, and then you minus 1. You pull that original exponent to the front, and then you minus 1 to the original exponent. That's how you get the power rule. Okay, so in particular, constants, or 1, I should say 1, I shouldn't say constants. So 1 prime will be x to the 0 prime, which will be 0 x 0 minus 1, 0 x to negative 1, which is 0. Okay, again, I'm trying to show you what all the formulas are true, and you know they actually somehow verify each other. And these are the formulas. So pretty much constants derivative is 0, and then multiply by a number, you can push the derivative inside. Addition, subtraction, you can give the derivative to the the parts of addition and subtraction. But when you're having a multiplication or division, you need to use those huge formulas. And finally, we have only, at this moment, I'm only introducing this formula for real functions, power of x. You pull the exponent to front as a coefficient, and then you minus 1 on the exponent. Now let's see examples. If I'm going to differentiate the first function, x squared minus 2x minus 1, well, I'll do dy dx, I guess. This is 1 term, 2 term, 3 terms. So it's a sum and difference. So I just do x squared derivative minus 2x derivative minus 1 derivative, where for the first, I pull the 2 to the front, I pull it here, and then minus 1, right? So I get 2x, 2 minus 1, minus, for 2x, it's a number, times the power, I pull it to the outer part, it will be 2 times x derivative. X is x to the first power, so I'm really getting 1x, 1 minus 1. And finally, 1, this is a constant. So constant taking derivative equals 0. And I'm getting 2x, 2 minus 1 gives me 1. So x to the first power is x itself, minus 2 times 1 is 2. X to the, this equals 0. X to the 0's power is 1. So this whole thing equals 1, which means I don't need to write any of them. And minus 0 is just nothing. So the answer will be 2x minus 2. The next example, y equals square root of x times 3x plus 5. Yes, of course, we can use product rule, but we don't have to. This, well, one of the things I'm trying to show you, well, I will be trying to show you throughout my packets is if there's a way you can avoid the more complicated formula, we avoid them. For example, here, instead of considering it as the radical x times 3x plus 5, you can consider it as a polynomial-like function because square root of x is x to 1/2, 3x plus 5, and then you just distribute. This will be 3x, by the way, that's first. When you multiply two powers with the same base, you add the exponents. So 1/2 plus 1 give you 3/2 plus 5x to 1/2 power. Notice this is y, okay? I did not differentiate yet. I'm preparing my original function to a polynomial-like form so that I don't need to do the multiplication rule. I don't need to do the product rule. I do pretty much polynomial. Then my dy dx will just be, I carry the coefficient, I take the exponent to the front, and then let me do the mess way. I take -1 from the exponent. Then again, I copy the sign, I copy the coefficient, I pull the exponent to front, and then I -1 from it. This gives me 9/2 x, 3/2 minus 1, which is 2/2, gives me 1/2, plus 5/2 x negative 1/2. Well, I would ask you to, rewrite your x negative 1/2 to at least 1 over x to 1/2 if you were in pre-calculus, but we're in Calc 2. I don't ask you to simplify everything to the simplest form. If you see an 2x plus 3x, yes, I do need you to combine them to 5x because, it doesn't really take much work. But when things are very complicated, I don't ask you to simplify everything to the simplest form, which is like, simplify as much as possible. You don't need to do that. This is perfectly fine for me. Okay. Next example, f prime of x equals x squared over 2x minus 4. So for this one, it's a quotient. Obviously, it's a quotient. I would be able to convert it into a polynomial-like if the single term x squared is on the bottom. Okay? But unfortunately, it's not. So there's no way I, avoid quotient rule. Because at the end, the last operation in this expression is the quotient. Okay, you pay attention to the last operation, unless you have a way to rewrite it. Otherwise, pretty much the last operation tells you what formula you are going to use. So if you have a quotient, you use quotient rule. F prime of x equals, this is f, this is g, right? So you do g, let me do this sideways. F over g prime is your g squared, the bottom, gf prime minus fg prime. So here you square the denominator first, then you copy that denominator one more time. Then you differentiate the numerator. Minus, copy the same thing you just differentiated or just wrote, times 2x minus 4 prime. Okay. Then the denominator is just a perfect square. I'm not going to do anything at this moment. And on the numerator, I'm going to deal with the two derivatives. 2x minus 4 times x squared, taking derivative to x minus x squared. Then my 2x minus 4 taking derivative, 2x taking derivative is 2. And minus 4, constant, nothing. Should I write 0? I'll write minus 0. And this gives me 2x minus 4 minus 2x squared over 2x minus 4 squared. As you can see, there are a lot of 2's here and there. So this is where I will ask you to simplify a little bit more. First of all, let's just, work out the numerator. This is, right, 4x squared minus 8x minus 2x squared over, on the denominator, I'll pull out the 2. 2x minus 2 is my 2x minus 4. Then the whole thing squared. So combine the like terms, I'm having this and this. Remember, a term has sign, number, variable. So you're having 4x squared and negative 2x squared. 2x squared minus 8x over 4x minus 2 squared. So this will be 2x times x minus 4 over 4x minus 2 squared. And then I cancel a 2. And I get x times x minus 4 over 2 times x minus 2 squared. That's the answer. Next example, f of x equals square root of 3. Well, square root of 3, there's no x, okay? No x means square root of 3 is a number, constant. It's an irrational number. If you look at, if you put in your calculator, it will tell you it's 1.732, etc. But the point is, square root of 3 is a constant. And it is constant because there is no x in the expression. So you can make things as complicated as you want. Pi squared minus 5 square root of 2 over, I don't know, sine pi over 5. No. Do you see an x? No. Then it doesn't really matter what this number is. It's a number. Constant. Its derivative is 0. So going back here, f prime of x is 0 because square root of 3 does not change when x changes. Okay, now you can try the practice questions number 1 and number 2. Keep going. The last thing, well, not last thing, but the next thing we're going to do is the chain rule. The chain rule helps us to find derivative of composition of functions. So f of g of x sometimes is written as f composed with g of x. Okay. And similarly here we have the prime notation and we have the ddx notation. Pretty much what it says is when you differentiate a composition of functions, what you do is you differentiate the outer one, then the inner one, then the inner one, all the way until the independent variable, the core of the changing, becomes x itself. Okay, and I would say in the beginning, probably you will use the U notation a lot because, that's more visualized. Like you can see how things works out because you are naming the middle variable U. But in the long run, I would say you will have to switch to the derivative version, or somehow, you need to avoid naming your U every single time. And when you don't name your U, pretty much you are using, even if you are using the ddx notation, you are not really writing dy, du, du, dx every single time. You will just do the derivative, whatever that is, times the next derivative, whatever that is. But right now, since we are going over our differentiation, I am going to write out what U is in the beginning. So chain rule actually is very powerful because it allows us to find the derivative of composition of functions, right? So with composition, you can pretty much make up a lot of different things with even just the basic addition, subtraction, multiplication, division, and constant, and power. Well, now the question might be, there are so many formulas. You have product rule, you have quotient rule, you have power rule, and you have chain rule. Which rule am I supposed to use when a function is given to me? You look at the last operation in that function. Okay, the last operation tells you what rule you are going to use. And you will see a lot of chain rules, because it's very rare you get such a nice basic function. So first example, we are differentiating 3x minus 1 to the fourth power. The last operation, parentheses goes first, right? So the last thing is really the 4. You're having a power, but you're not having a power of x. So where x supposed to be becomes 3x minus 1. So you ignore the last operation, in this case, raising to the fourth power, and everything before that is your u. Take away my box. So since the last thing is raising to the fourth power, before that, this will be 3x minus 1 will be my u, and then y will be u to the fourth power. Then I'll use the the dy dx chain rule. This is literally dy du du dx. You can imagine this is a multiplication where du cancels each other. So the dy du is differentiating this function with respect to u. This is a power, u to the fourth power, right? So I pull the exponents to the front and I minus 1. Then du dx, I'm looking at u as the function and x as the independent variable. And when I differentiate that, I'm having 3, x is gone, minus 0. So this is 4u third times 3, which is 12u to the third power. You cannot stop here, because what they gave you was 3x minus 1 to the fourth power. There's no u. You named u. Nobody else knows. So you need to give it back to x. U is 3x minus 1. Okay, that's how you use chain rule. Next example, square root of x squared plus 1. So the last operation is taking square root. Then everything before that is your u. That's u. Okay, but again, I'm going to do some preparation because we don't like square root. We like to call it x squared plus 1 to 1/2. Then, well, I'll make my f of x equals u to the 1/2, which means u is actually x squared plus 1. Again, the logic is here. It's this way. Last operation, I keep it. Everything before that, I call it u. That's why I knew it's u to 1/2 before I know what my u is. Okay, I know it's u to the 1/2 because 1/2 power is the only thing I will keep. Then I compare them. U will have to be the x squared plus 1 that set in that base. Then my df dx is df du times du dx, where I get the f du from the equation between f and u, and then I get my du dx from the equation from u and x. df du 1/2 power u 1/2 minus 1 times du dx x squared 2x 2 minus 1 plus 1 is constant 0. So I'm having 1/2 u to negative 1/2 times 2x. And I'm giving u back as what it really is, x squared plus 1 to negative 1/2 times 2x. Well, I could have canceled them here, but I didn't, so I'll cancel them here. This is x times x squared plus 1 to negative 1/2 power. Yes, you can write it as x over, if you want to, but I don't really ask you to do that. This is perfectly fine. X times x squared plus 1 to negative 1/2. Next example, my f of x equals 5x minus 2 to the 4th power times 6x minus 4 to the 8th power. What is the last operation here? It's a power and another power, and between them, nothing, which is a multiplication. So my function is a product. My f is a product of the 4th power of 5x minus 2 and the 8th power of 6x minus 4. But the thing is, the last operation is multiplication. So my f of x is a product. If I'm differentiating a product, I use product rule, which means my f prime will be first factor times the second factor differentiated plus the second factor times the first factor differentiated. Oops, sorry. Then I work this out. By these, I mean the derivatives, the first and the second. Okay, so 6x minus 4 to the 8th power, I'm differentiating it. When I differentiate a power of something, so pretty much this is my u, right? And we do this, which is called general power rule. When you differentiate a power, you first pull the exponent to the front, and then, pretty much you are keeping that u, or whatever the base was, to 1 power lower. But if what's set on the denominator, set on the base is not x itself, you need to differentiate, pretty much follows by du dx, which will be the base differentiated. So 8, 6x minus 4 to the 7th power times 6. Okay, this gives me 48, 6x minus 4 to the 7th power. Now I do the second thing, the second derivative to the 4th power, then derivative. Same thing, I'm differentiating a power. So I pull the exponent to the front, I lower the power by 1, and then I differentiate the base. So this is 4, 5x minus 2 to the 3rd power times 5. And this gives me 20, 5x minus 2 to the 3rd power. Then I bring both of them back to my derivative. Equals, I have 5x minus 2 to the 4th power times 48, 6x minus 4 to the 7th power plus 6x minus 4 to the 8th power times 20, 5x minus 2 to the 3rd power. Okay, so I'm pretty much plugging in what this derivative is, and I'm plugging in what this derivative is. I computed them down there, right? So these. Then I just write them a little bit nicer. I'm not going to factor out the common factors. I could, but I don't want to. So 48, 5x minus 2 to the 4th power, 6x minus 4 to the 7th power, plus 20, 6x minus 4 to the 8th power times 5x minus 2 to the 3rd power. Okay, so as you can see, and as you should know, when you start with, well, somehow complicated function, right? Somehow complicated function. And taking derivative really makes things complicated very fast. So you do expect to have huge expressions. Okay, now you can try practice number 3 and number 4. Last thing in this lecture, we don't just have derivative. Because taking derivative give you another function. So you start with f, you take its derivative, you get a new function f prime, which is a function. Then you can say, I want to find the derivative of f prime. Then you get the derivative of the derivative. And then you can say, I want to find the derivative of derivative. Okay, so you can keep differentiating and keep getting the derivative of the previous function. And that's the higher derivative. So the nth derivative of f is pretty much you differentiated n times. And we have the two notations with ddx and also with the primes. Normally I think, personally, I probably will write up to like triple prime. So the third derivative, I probably will still write, this is the derivative of the second derivative. But I wouldn't really do this. This probably I'll write like a 4. This is f3, which means f triple derivative differentiated. But with ddx, you can write 10 if you want, This is the 10th derivative of y to the x. Okay. So how do you get higher derivatives? Be patient, get the first derivative, then get the second derivative, then get the third derivative until you get where you need. And this is an example to pretty much show you how differentiating higher derivatives work. So I gave you this, basic chain rule function power, or general power rule, whichever you call it, the third power of 4x minus 2, and I want to find f of 1, f prime of 1, and f double prime of 1. What are they? So pretty much it is, in terms of, algebra, they are the value of f when x equals 1, and the derivative of f, the new function, when x equals 1, and then the second derivative of f when x equals 1. But also you can imagine your f of x is the particle displacement, then this will be f of 1 is when t equals 1, where x equals 1, where it is. F prime of 1, the velocity, pretty much speed, and f double prime will be acceleration, all at t equals 1. Okay. Anyway, let's get into the calculation. F of 1, you just plug in 1. 4 times 1 minus 2 to the third power. This will be 2 to the third power, which is 8. Now f prime of 1, you need to find f prime first. So just like if you want to find f of 1, you need to know what f is. You need to, if you want this, you need the expression of f prime of x first. So what's f prime of x? General power rule. 3, 4x minus 2. You pull the exponent to the front. You lower the exponent by 1. And if the base is not x itself, you differentiate it. So this will be 3 times 4x minus 2 squared times the derivative of 4x minus 2 is 4. X gone. Minus 2 constant 0. So this is 4x minus 2 squared. Then I can plug in 1. F prime of 1 is 12. 4 times 1 minus 2 squared, which will be 12 times 4 minus 2, 2 squared. And that's 4 times 12, 48. Now f double prime, same thing. If you want to get f double prime of 1, you need to get f double prime of x, which is 12 4x minus 2 squared prime. It's f prime prime. And this is 12 times. You pull out the coefficient and then you differentiate that power. You pull the power, the exponent out, to the front. You lower it by 1. And since the base is not x, you differentiate it prime. So we get, I'll multiply them, 24. 4x minus 2 to the first power times this equals 4. So this is 96. 4x minus 2. Then I can plug in 1. This equals 96 times 4 times 1 minus 2, or 96 times 4 times 1, 4, minus 2, 2. This will be 192. So we have 8, and then we have 48, and then we have 192. Okay, that's it for this lecture.